Okay, so one more problem in homework number 19. We're getting near the end. That's great. Isn't that great? I think it's great. All right, let's see. We have this doohickey gizmo thingy with two identical slender rods. They're held together by this cable, and we have this external moment being applied to it. And these are 1/2 meter each. They're both 10 kilograms. The angle between them is 120 degrees, and the external moment's going counterclockwise is 100 Newton meters. This thing's in the vertical plane, so gravity does play a part. And we, at this instant shown, the angular velocity is 0. And we want to find the angular acceleration of the assembly, and we want to find the tension in the cable. So here we go. I didn't write down what my find was, so find. And we're looking for A, angular acceleration, and B, the tension in the cable. I'll call it FT. So, good place to start. Let's get the moment of inertia of each piece, right? I could get it from the entire assembly if I wanted to, about A. 1/2 dozen one, 6 of another. Not sure it would save me any time, and later on it's going to be useful to me. So each bar is identical. So they're going to, moment of inertia about the individual centers is going to be the same. And it's a cylinder rod, so it's 1/12 ml squared. So 1/12 10 times 0.5 squared, and I happen to have the number already out there, so that'll make things a little quicker than some of my other videos. So we have 0.20833. I don't know why I have 2 3s in there. I don't know. I guess I decided to go 5 sig figs. All right, and so the first thing I'm going to do is a little bit of geometry and kinematics. That's supposed to be an M in there. I misspelled kinematics. Kinematics. And draw a line underneath it. Okay, so I am going to, so first for the geometry, I want to get some angles, or just to make sure, get some angles straight here. Redrawing the thing. Always a good idea. Make extra sketches. More sketches can lead to better understanding of stuff. Trying to skimp out on the sketches is where you'll get confused. So I say more sketches. Okay, so this is 120 degrees right here. So that means that this angle and that angle, and these are equal to each other, so that angle has to equal that angle. And if it's 120 degrees, I think I decided to call this angle, well, another thing we can note is that that angle has to be the same as this angle right there. Okay, and I decided to call that beta. So writing the thing out to the side, the 180 minus 120 and divided by 2 will give us 30 degrees, right? So that right there, and it looks like 30 degrees because we tried to draw it pretty close to being what it should look like, right? And there you go. Also, another angle we might want to have right here is this guy right here, and we can see, I'm going to call that phi, I think. Let me see. Let me look that up. I want to know, so just I get a couple confused. I can't remember certain Greek letters for whatever reason. So like this little mental block. I don't know. I don't understand. I don't know. But that's neither here nor there. Anyway, so that's 60 degrees, right? So it's 180 minus 120, so that's 60 degrees. I want to find the distances to the centers right here. It's just gonna help me. I could do it now or I could do it later. And that's going to get in my way. So I'll make him a little smaller, and I'm going to want to know the distances to the center right here. So I want to know that one, I want to know that one. I'm also going to want to know this guy right there. Later on, I think I'm going to want to know that distance right here. So I decided to call this G1 and this G2, right? So they're center of gravities. And I think I also messed up by putting the letters right there because I'm going to want to draw arrows in a minute. So I'm going to put it right here, G1, and I think G2. Yeah, that's a good spot for it. I won't get in the way. So the distance, I'm going to call this one, and this is A, and this is B, and this is C, of course, right? So I'm going to get this X distance. I decided to call this X AG1 right in there. And I'm going to call this distance, obviously, maybe not obviously, XAG2, right? And I think I decided to call this XBG, staying alive, 2. All right, and then lastly, I think I'm going to call this YAG2. All right, so that's going to be the vertical distance right there. And that's just going to be useful to me later on. That's why I'm doing these. Also, because I said this is kinematics, this is also the geometry, I'm going to have my, I'm going to assume that my angular acceleration, alpha, is going to go counterclockwise. That would mean that this guy right here, which I'm going to call AG1, is going upwards. And I'm going to call it AG, right? Because I also, if it's coming up this way, we'd actually have the, so let me put it this way. The acceleration here would be perpendicular to the line between here and here, right? So we would be going upwards, and I'm making it just a little very faint little line like here. But it's going to be easier for me if I take the acceleration in the x direction. So that's going to be the acceleration. Oh, I started writing G when I meant 2, right? That's going to be the acceleration of G2 in the x direction, and then this right, the acceleration of G2 in the y direction, right? And those two together will equal that acceleration, right? But it'll be easier geometrically or mathematically just to find that. And we'll see that in a second. But first, let me give me these dimensions. So I'll start out with my XAG1. It's just going to be simply LAB over 2, right? Or 0.5 over 2, which is 0.25 meters, right? Now let me get, what do I want to do? I'm going to go XAG2, and that's going to be LAB, this length, plus this little length. So maybe I actually want to get, let me get this one, so then I can add, then I can just add LB and that one together. So I will get the XBG stained lab 2 equal, I know, I'm a juvenile. That's going to be LBC divided by 2 is that length hypotenuse times the cosine of that phi. So that's 0.5 over 2 cosine of 60 degrees, and I'll set it down here below the thing. I believe we're going to get 0.125 meters. So if I want to have XAG2, that'll be LBC plus XBG stained lab 2, or 0.5 plus 0.125 meters And I guess I'm going down to the next line, 0.625 meters. And then the last one, I want YAG2. And that will be my LBC over 2 sine of phi, or 0.5 over 2 sine of 60. And that should be 0.2165 meters. All right, so I'm going to use those with the kinematics here, so I can find the acceleration of G1y is simply going to be alpha x AG1. The acceleration of G2x is going to be alpha y AG1, right? You can picture that, right? This thing's going this way, so that makes this thing go that way. And then x G2y, this one, alpha times x AG2. All right, so we got a lot of preliminary stuff out of the way. The next thing I'm going to do is get my FBD and IBD of the assembly. Now, I don't want to. I'm going to draw it large enough that I don't have to cram everything in there, but there we go. And I'm drawing the entire assembly. And let me draw it over here too. Kind of made that one a little longer than the other one. I'll cut that a little bit. And we'll put the cable in there. All right, so now I want to get the loads. And here, I'll declare what my directions are going to be here. All right, so acting right here, we're going to have a reaction at A in the y direction. And I'm not asking for this. I did originally, but just made the problem longer. Didn't make it to be any longer. So I'm not asking for these, but we do want to put them on there. We do have this external moment that we want to place onto there. We could put that actually moment can move anywhere we want to, but that's I think it. I think of it as being like a motor or something that's attached to this pin and that's driving the whole thing. That's my way of looking at it. And let's see, we'll have our M, and this is going to be AB, yeah, AB times G right there. So that's our gravity acting against me. And then here is going to be our BC times G. All right. So I think those are all the external loads. Now the tension doesn't go in there because it's internal. The cable is part of the assembly, so we don't see it. Now here are these two pieces, and each piece needs to have all of the effective moments on it right here. So first one, we're going to have this guy right here. So he's going to go M AB, acceleration of G1Y, right? We're also going to have a rotational one right there of I AB alpha. This one will have an acceleration in this direction, mass BC, acceleration of G2 Y, and MBC, acceleration of G2X. Now, this doesn't have an X because this thing's not rotating. right? So, I mean, it doesn't have an angular velocity. Its angular velocity is 0, starting from rest. So if it was rotating, it would have a component in the x direction here, and then there would be an additional component in the x direction of this one. But actually, it would be a component that would be going from here towards there. So they would have a portion of it would be in the x direction, and a portion of it would be in the negative y direction onto these pieces. And it's kind of better to keep them separated because we don't know what that alpha is yet, right? But we simplified this problem by not having those in there. All right, so, oh, and we forgot this. This too is rotating BC alpha. Now remember, it's not spinning like this, it's spinning as part of the whole thing. But because it's part of the whole thing, everything, it has the same angular acceleration everywhere. So it feels that rotation, just like that one feels that angular acceleration rotation. Okay, so the sum of the moments is equal to the sum of the effective moments. And we're taking it about A. And we're taking it about A specifically so that we don't have to find out what these reactions are. If we took it about the center or something else, we would need to have that reaction. But here's our strategy by getting rid of them. So starting here, we have, I'm going to go by symbols, even though it takes me a little longer. Okay, so, and by the way, this counterclockwise is positive. So we have that moment, applied moment, minus MAG. All right, so I need to actually, this is going to take up a lot of space, so I'm going to go cram it over to the left. Will be a better idea, so I'll have that. Mine M, I'm going to make it nice and neater, a little neater, put it right on the line, minus MAB G times the distance, which is XAG 1. Then I come up to this one. This one's also clockwise, so it's MBC times G, and that's going to be XAG2. And those are all the loads on the left-hand side, so they're going to equal, and then everything over here on the right-hand side is, I'll start out with this, IAB alpha, and I'll go this guy next, so it's going to be plus MAB my mind is wandering. A G1Y, focus, times our X, that should be AG1, and then I'll go this one next, plus I BC alpha, and then I'll do this one next right there. Now I'll do this one next, plus MBC AG2Y, and that's going to be times this distance right here, yep, XAG2, and then I have I'm going to cross over the line, I know, this last one right here, so I'm going to go plus MBC AG2X, and that's going to be times this distance, YAG2. There you go. Whee! That's a lot of stuff. Because it's going to be filling some things in, I'm going to go to the next page. All right, so next page, and let's take a look here. Page 6. Let's put some values into there. So this is 3 continued. So with some values, we have 100 was the external moment. minus the 10 times 9.81 times that distance that we got, and that distance of AG1 was 0.25, minus 10 times 9.81 times AG2, 0.625. It's going to be equal to I, which was 0.2083. I didn't need the extra 3. Alpha, we don't know alpha, plus 10 times AG1Y. We're going to replace that AG1Y with alpha and XAG1. So XAG1 is 0.25, but we're not done. Remember, we also have to do XAG1 here again, right? So there was an XAG1 because this was alpha XAG1, so we have this. So it's actually, this becomes squared right there, right? Now we're going to go add, and we're out to this line right here, so I'm going to come all the way over here maybe. 0.2083 alpha, right? So it happens twice. This is for this member, and this is for that member's rotation. We have plus 10 AG2Y. AG2Y is alpha times XAG2, 0.625. Right. Points, and then times XAG2. So XAG2 is again this right here, so it ends up being squared, right? That's the same. But now I'm going to double check something. I think I might have messed something up. Let me double check. Yeah, I think, yeah, no, I'm okay. I'm on the right track. So go plus this last one, 10, and then AG2, which is going to be, no, what, whoa, did I mess something up? Yes, I did. No, in the X direction. Okay, so it's going to be alpha YAG, which we know is 0.2165, and that times YAG, so it ends up being squared. All right. We do all of this, and we have alpha as our main guy. Alpha, and that alpha I've already calculated out to be 2.615, and it ends up being positive. So we chose this alpha. I chose that initial alpha correctly. I chose that alpha because it was the positive direction, but this weight, these weights might not have been enough to overcome this moment. These weights might have been enough to overcome this moment. This moment might not have been large enough to make it so that the thing would accelerate counterclockwise. It could have accelerated clockwise even though it had that moment on there. Depends on the magnitudes of it. And in a previous version, I did that, and the values that I used actually made this cable go slack. Right, so I ended up getting a negative cable, so it became a more complicated problem. But there was enough; it was sufficient enough to keep the cable tight that I found, that we'll see. and we could take you could fast forward right now if you want to, but I think I want to show you that this right here could have been done a little simpler. This portion right here, if I just had found the moment of inertia initially of this assembly about that point right there. So let me go here and say that this is I'm trying to think of the word that I'm trying to alternatively. There we go. I don't know why I couldn't remember the word. Alternatively. ... We could have found the moment inertia of the whole thing about A. How would we do that? Well, first we would take the moment of inertia of AB, then we would add to it the mass of AB times LAB over 2 squared. I didn't draw that very nicely, right? Because that's the distance we would have to move, right? So this is the moment of inertia of this, but moved over there. Now we have to do the same thing from here, and we're going to have to play around a little bit with when we go for that distance right here. Interestingly enough, we'll have to have that distance squared, but we'll go plus IBC right there, and say plus MBC, and now this is going to be kind of a long thing because I need this diagonal distance. And notably, when we get that we would take the sum of the square root of the sum of the squares, but we're going to square that thing, right? So we don't need to take the square root of it. That's an interesting part. So the distance, what we would have there here is xag2 squared plus yag2 squared, right? This and that. I think I'm correct in this. Let me double check something. Yes. So what we'd be left with is 0.2083 plus 10 times our 0.5 over 2 squared, right? Plus 0.2083 plus 10 times, and now we have this squared, which we found to be xag2 was 0.625 squared plus, and then y 0.2165 squared. So what we would be left with is 0.2083 times 2, boom, and then that's a 0.25 squared times 10, and add it, and then we're going to have 0.625 squared and 0.2165 squared, add them together, multiply by 10, and then add them. So we have 5.417 kilogram meter squared is the moment of inertia of this. So instead of doing a free body right here, right, the FBD or the IBD of this would simply be, and I'll draw them small, I'll redraw them, FBD, IBD of this. Right there. And here's our reactions. Here's the external moment. Here are we still have M, A, B, G. we still have M, B, C, G. All right. Is there more lead in that? You suck. There you go. I think this one's still good. Yeah. But now over on this side, we simply have IA alpha. So if we take the sum of the moments about A is equal to the sum of the, and actually in this case, because it's that special case where it is about a fixed point, we can go IA alpha. That's all we have to do. Right? And that's what the thing becomes. So we have all that same stuff that's up here that happens right there. So, you know, I'm good, with the risk of being, I don't feel like writing the whole thing out, but I'm going to do it anyway. 10, 9.81, 0.625, and that equals 5.417 alpha. And if you do all of this, you also get alpha 2.615. You can calculate it yourself to double check, right? And I'll write same. Boom. Okay, so carrying on here, right? So we got that first part. Now we need to get the tension in the cable. In order to get the tension in the cable, we need to do another FBD and IBD, but this time of only one of the pieces. So just this one by itself. So we're going to take the sum of the moments about B, and we're going to cut the cable, and so we're going to be able to see what the cable tension is. So we can't see the cable tension until we've cut it. It's internal, right? So I'll place these guys in here, draw them in, and the cable tension is going to be like this right there. And we'll call that FT. And we'll have a reaction at the pin, RBY. And we don't know that. We don't want to know it. So that's why we're taking some of the moments about that. And there is no moment about the thing. It's a pin. But there is weight. So we're going to have MBCG acting right there. And now we cannot do the thing we did right up here. This up here is only when you're about a fixed point, and this is not rotating about a fixed point. This one is actually translating and rotating at the same time. What we can do, it is going to be these effective moments, or these accelerations happening onto this piece right here. So, and I think I'm going to calculate this over to the side, by the way, but we're going to have that acceleration and that acceleration happening. So we have MB AG2Y and MB AG2X. These two things are equal to each other, and here's X and here's Y. And it's all about the center of gravity of the thing. This also still has the BC alpha. Over to the side over here, I'm going to find my AG2X. Remember, is alpha, and it's YAG2. So we have 2.615 times that YAG is 2 losing track. This guy 0.2165. And so I got 0.5661. meters per second squared. And then we can also get, so that's the x direction. We can get the y direction, g2y alpha, and now that's the xag2, 2.615, and I got 0.625 for this. So we're left with 1.634 meters per second squared. We're getting close to the end. And okay, so we're going to take the sum of the moments about B is equal to the sum of the moments about B effective. And so looking down at this, okay, we need a little bit of geometry here. So I didn't make that look horizontal enough. It's going to be a little bit more like that. This right here is beta, but also that's beta if you remember from the initial geometry of this piece. So if we want to have the moment due to this unknown tension, and it is going counterclockwise about this point, it's only the part of this tension that's perpendicular to this line right here. So it's going to be this that times the sine of 30 degrees. And times the length of this piece, I guess I did, okay, so I'm going to keep it as symbols. I guess I'm going to have to go through the next page because I'm going to run out of space. It's because I did this part up here. I did that extra thing. So I'm going to go LAB. All right. Now we're also going to have this guy, which is going clockwise. So it's going to be MBCG. And this distance right there, actually from before, is that XBG2. And those are all the loads on the FBD. So we come back over to here, and we're going to have our I, BC, alpha. I'm going to keep these because I want to make a point in just a second. We're going to have our MB, AG. No, I'm going to replace that. Sorry. Let me do this in one step. AG2X, AG2X, which is going to be alpha YAG2 times the YAG2, right? Because that's the distance. So it ends up being squared. Fine. The next one here, this guy, we're going to go plus MB AG2Y. AG2Y is alpha X AG2 right here. But we want to go the distance here. And you're going to go, oh, I'm going to square that. No. It's going to be only that distance right there, because this is the distance. Remember, this is the acceleration. Here is the moment, so it's xbg2. And there lies the difference between doing, in this case, about the pin. This would be squared if it was pinned about, rotating about the pin point, but it's not. It's rotating about a point other than the pin point. So it's actually a different value. So that's like an important thing to note, that this can't be done by simply writing this equation. It has to be the effective moments, because it's this part is translating and rotating, not just rotating. So it seems like a small thing, but it's what, you know, the actual motion of the piece. So we take that FT, take the sine. This is 30 degrees. This thing is 0.5 minus, and we go 10 and 9.81 at XBG2. Where did XBG2 go? XBG2 is 0.125. Moment of inertia here is 0.2083, right? The alpha, we know the alpha, and the alpha is going to be 2.615 plus 10. I guess I'm going to keep the alpha in here because I have it written right there. 2.615, and then YAG2. So I guess I didn't actually need these up here. That's all right. I was trying to make my point up here. I calculated those, but I didn't actually need them because of the way that I wrote this here. If I keep true to what I've just written, I didn't actually need those values up above. But maybe it highlighted what maybe. I don't know. So YAG2 it comes out to 0.2165. It's right there. Oops. Squared. And then lastly, 10, 2.615, XAG2 is 0.625. XBG2 is 0.125. We do all of that, and we're going to get FT is going to be equal to 64.30 newtons. So maybe I will be able to conclude this on this page. There you go. Answers. A, alpha, and it's actually a vector because we're going to give it direction, is 2.165 radians per second squared counterclockwise, and B, FT is equal to 64.30 newtons tension, because you can't push a rope. And we'll box it in. Whoop. That's sad. That's just sad. Okay. The end. 43 minutes. Wow, long time, but it's worth it.